Greetings. We will discuss the variational principle in today's class. And this is a very beautiful principle with applications across physics, and it is at the very foundation of describing the laws of nature. The greatest contributors to this are Lagrange and Hamilton. And let me begin with a question that if you have got objects with such shapes, so there are four objects over here. You see the one in the front. So this is like a wooden track. And if you let a marble go at this point, it is going to roll down along this track and get to the point B. And this will happen under gravity and no other force. Okay, so you release it from rest at 0 speed and just let go and determine the time it will take to go from point A to point B. But you can let it go along a different slope. You can let it go along the slope of this other track which is placed behind the first one. So these are narrow tracks packed one behind the other for the sake of this picture. And there is a third track which goes like this, and a fourth track which is just the straight line between A and B. And one can ask, along which track would the marble reach the point B in the least time? Okay, will it be along the straight track or along one of the curved tracks? And if it is one of the curved tracks, there can be infinite curved tracks depending on the depth and the slope and the curvatures, right? You can have literally infinite tracks. So which of these paths will give you the correct slope? And this is the variational principle, and it's a very fascinating principle. And here I quote from Richard Feynman, who was led to the variational principle by his high school teacher. And high school means he must have been a young boy, and being exposed to the variational principle at such a young age, Feynman got into addressing some very important and fundamental principles in physics, which is the principle of least action. He found it very fascinating, and in fact, subsequently, he went on to develop the path integral approach to quantum mechanics, which is actually based on the variational principle. So this was developed by Feynman. And what the variational principle does is to explain, or it sort of accounts for everything that happens around you, all the mechanics, all the dynamics, as to when things happen, an object falls, or when you throw something, it takes a particular trajectory. The moon goes around the sun, around the earth goes around the sun, right? And all the planetary motion, all the galactic motion, and even these larger motions which take place, whether it is small or big, how vehicles move, how rockets fly, their trajectories, automobiles, bicycles, soccer ball kicked around, okay, any motion of any object from the very small to the very large, okay, most of it is accounted for. It is, this principle describes it. I will make a distinction between the words explains and describes. Explains is to give a reason. Describe is to provide a detailed, accurate description how it happens. Explain would answer why it happens. So we are going to discuss the question why. We are not going to discuss the question why, we are going to discuss the question how. Okay? How do things happen the way they do? How does water flow, and then it meets at a particular point? Okay, there is a confluence of rivers, how it flows down the mountains, the streams, the path that water takes, and so on. So all of these questions in mechanics are accounted for by this principle. And we are accustomed to accounting for this mechanics in terms of the Newtonian mechanics, which is the Galileo-Newton approach. So the law of inertia, which is common to the principle of variation also. But then subsequently, in the Newtonian approach, you invoke the principle of causality and determinism, that equilibrium is disturbed. And this happens in a manner which you describe it by saying that the rate of change of momentum is equal to the stimulus, which is a force. So you invoke the cause-effect relationship. Acceleration is the result of the force, and it is proportional to the stimulus, F equal to ma. So that is how you account for motion in Newtonian mechanics. Variational principle is an alternative way of providing that description. It is completely equivalent, it produces the same result, but it makes no use of the idea of force. So the principle of causality and determinism is totally abandoned in this approach. And this is really interesting, that you start with something very different, but you get the same result. Okay? So this is the variational principle that we are going to discuss, and this is of course taught in a good number of MSc courses, for example. But then there are recommendations in the last 15-20 years that this should be introduced early on in college education. There are very nice articles which I have referred to over here, getting the most action out of the least action. Okay, so this is a nice title. You really don't need very advanced calculus or anything to do that. Elementary mathematics is sufficient. And these are some nice articles which I would like to suggest that you read up. And as I mentioned, the variational principle, it provides a backward integration of classical mechanics to develop quantum mechanics. So it's not that quantum mechanics can be derived out of the variational principle, but the variational principle, which is the path integral approach to quantum mechanics, it is one way of introducing quantum mechanics. It's completely equivalent to the Schrödinger and Heisenberg formulation, but it uses a different path. And this path is somewhat fascinating because it also provides a foundation for classical mechanics. So from the conceptual point of view, the development of quantum theory using the variational principle is really very fascinating. And this was done by Feynman, as I mentioned. It was based on a suggestion which Dirac had made, and Feynman worked on that suggestion intensely and ended up developing this alternative approach to quantum theory. So the history of the variational principle is pretty old. Actually, it goes back to the 17th century when Fermat accounted for the paths that light takes, because when light rays meet an interface, it changes the direction, okay, unless it is normal to the surface. But then if it lands obliquely, then it gets reflected, it can get refracted, okay. And why does light take the path that it does? How do you describe it? Is there a governing principle which will describe this accurately? So this is what we find in the Snell's laws, for example. You can give a detailed account for it using Maxwell's equations by invoking the interface conditions of the electric and magnetic fields. So we will discuss this at a later point in the course. But then Fermat accounted for it in terms of what is called as the principle of extremum action. So he formulated this principle that the time the path light would take is an extremum, and that accounts for the trajectories of light rays that we see in reflections and refractions. So there were other contributors to the development of this field. Maupertuis and Euler made very significant contributions. I will mention the Euler-Lagrange equations a little bit later, and of course Hamilton as well. So here I want to emphasize once again that most questions in physics really boil down to finding an accurate way of describing the law which accounts for your observation. So it doesn't tell you why the acceleration is proportional to the force. Okay? But it tells you that if equilibrium changes, you know that there is a rate of change of equilibrium, rate of change of momentum. How do you formulate the law which accurately describes it? And that law in Newtonian method is F equal to dP by dt. Now this would explain the dynamics of everything which undergoes a change in equilibrium. Every single thing, whenever you see that there is a change in equilibrium, it is accounted for by this particular law, which is why you call it as a law of nature. So it is not telling you why F is equal to dP by dt, but it tells you that whenever equilibrium changes, what is the law that describes it accurately? So we are going to answer these questions as to how do you describe the law? You know, what is the principle, what is the governing principle which tells you how things happen the way they do, and not really why they happen the way they do. Sometimes we use this vocabulary loosely, but then we have to keep it in mind that, okay, this is the real question that we are really trying to answer. So the alternative formulation of mechanics, of classical mechanics in terms of the variational principle is best done in terms of the generalized coordinates, which are the generalized degrees of freedom that we talked about in the previous class. And we know that when there are constraints, you can reduce the degrees of freedom. So an n particle systems which will have 3n coordinates, you really don't need all of them to describe it because of the constraints if it is a rigid body. Okay, or there may be other kinds of constraints. So this is just one example that we discussed only in the previous class. So depending on the nature of constraints, you have to deal with fewer coordinates, and the variational principle is best cast in terms of these. So these are the generalized coordinates which we discussed in our previous class. And if you look at how light travels, okay, if you have parallel rays incident on a parabolic reflector, okay, they all get reflected and converge at the focus. Okay, if you have a light source at the focus of an ellipse, and if you have an elliptic mirror, then the light waves will bounce the way it is shown in this figure. It will always go through any point, wherever it hits, it will go through the other focus. Okay. So here is a picture of this giant meter wave radio telescope which we have near Pune, and this also has these parabolic reflectors. So here we can ask, why does light take the path that it does? This is one question that we can ask. But then, is this the right question to be asked? Or is the right question, how do you describe the law which tells you how light propagates? So these two are somewhat different questions. And it is the question B which is the right question to be asked. So what is the law which describes how light propagates? And we will tackle this question. We begin by the description of the state of a system, and then we have to determine the law which would describe accurately how the state of the system changes with time. So how do you characterize the state of a mechanical system and how does it change with time? So these are the questions that we try to answer in mechanics, and Newtonian mechanics does it invoking the cause-effect principle of causality, and this is contained in the laws of Galileo and Newton. Galileo's identification of the law of inertia, which helps you find what is the inertial frame of reference, and then Newton's law F equal to dp by dt, which tells you how change in equilibrium is accounted for. And in Lagrangian and Hamiltonian mechanics, which are founded on the principle of variation, the formulation is again in terms of the state of the system, which is described by position and velocity, or alternatively by position and momentum, or equivalently you can describe the state of the system by a function of position and velocity. So L is a function of position and velocity. We will discuss what this function is. Or you can have a function of position and momentum, which is h. So L is called as the Lagrangian and h is called as the Hamiltonian. And you can describe the state of the system accurately either as position and velocity or some function of position and velocity, which is by Lagrangian. So in the variational method, you describe the state of the system by the Lagrangian of the system, okay, or equivalently by the Hamiltonian. But Hamiltonian you would write in terms of Q and P, and Lagrangian in terms of Q and Q dot, which is position and velocity. And then we have to set up the equation of motion, that how does this system change with time. So you need the time derivatives of the position and momentum. So the time derivative of momentum is the force in Newtonian mechanics, and likewise we will see how the system evolves with time in the Lagrangian formulation and in the Hamiltonian formulation also. You will get the rate equations for position and momentum in the Hamilton's formulation, but as we develop this further. So these are the equations of motion. So just like F equal to dp by dt, we are going to get these equations. So this is the equation of motion which tells you how does the system evolve with time. So how is the system described? It is by position and velocity or position and momentum. Okay. How does it evolve with time is given by the Lagrange equation, which is the equation on the left, or by the Hamilton's equation, which are the rate equations, and you have the time derivatives involved in these equations. It tells you how the system evolves with time. Actually, the question remains the same even when you reconcile yourself with the fact that position and momentum cannot really be accurately simultaneously measured. Okay, if you make an attempt to do so, that attempt fails. There is no method. It is in principle impossible to get accurate simultaneous information about this. And if that is going to happen, then this whole system is going to collapse. Okay, you need an alternative way of describing the system. You cannot describe it by position and momentum. You have to describe it by something else, and you describe it by a state vector, and then you describe how it evolves with time, what is its time derivative, which turns out to be the Schrodinger equation. So in all of these, you see that the basic question is the same. How do you characterize the state of a system? It is in terms of position and velocity in classical mechanics, and it is in terms of a wave function in quantum mechanics. Okay, so by mentioning quantum mechanics, we are slightly jumping ahead of ourselves, but this is just to keep this at the back of our mind, that the fundamental question in physics is this, that how do you describe the state of the system and how does it evolve with time? How does it change with time? So it's the same question that you answer in Newtonian mechanics, Lagrangian mechanics, Hamiltonian mechanics, Schrodinger mechanics, okay, which is equivalent to Heisenberg mechanics and also to Feynman mechanics, which is the path integrals in quantum mechanics, path integral approach to quantum mechanics, right? So we started out with this question that if you have got a point S, okay, which is the start point, and a finish point over here, and you let go of some marble over here, what is the curved, which curve would give you the fastest reach. Okay, you let go of this particle and you are asking along which particular curve the object will reach the finish point fastest. And chronos is the Greek word for time, fastest is brachistos. So you are asking what is the brachistochrone, okay, along which curve do you have the brachistochrone. So this problem is famously known as the Brachistochrone problem. This was actually posed by Johann Bernoulli and in the 17th century, and the tradition was that learned people would throw an open challenge that, okay, this is the question that I'm asking, do you have the ability to solve it? And look at how he posed it. He says that I, Johann Bernoulli, address the most brilliant mathematicians in the world. Nothing is more attractive to intelligent people than an honest, challenging problem, whose possible solution will bestow fame and remain as a lasting moment. So this is the problem that Bernoulli posed. And he says that if someone communicates to me the solution of the proposed problem, I shall publicly declare him worthy of praise. So that praise coming from somebody like Bernoulli would really mean something. And there were 5 solutions which were offered to this problem. One was by Isaac Newton, then by Jacob Bernoulli, who was a brother of this Bernoulli. Bernoulli, when you talk about Bernoulli, there are so many Bernoullis in 3-4 different generations, some sons, cousins, nephews, and so on. And all of them were brilliant. So it was an extremely brilliant family. And then there was a solution offered by Leibniz, by Delay Hospital. He's the one after whom there is a formula which is well known, and then Johann Bernoulli had a solution himself. Newton did not actually identify himself. He offered the solution anonymously through somebody, okay? But then Bernoulli, when he saw the solution, he recognized that this must be Newton's, and he said that we know the lion by his claw. So this has got a very interesting history, the development of the variational principle and so on. So what is this principle? It begins with an ansatz. An ansatz is like an axiom. Okay, it is some consideration that you begin with to develop your theoretical formulation. Okay, so Newtonian mechanics, for example, develops with the ansatz that, okay, you describe the state of a system by position and velocity, or by a point in phase space. It can be the position velocity phase space or the position momentum phase space. And the system, the equilibrium is disturbed according to the principle of causality. You don't derive it from anything. You propose it as an ansatz. You test it. And you find that, okay, everything happens according to it is consistently described by this ansatz. And that is how you test the theory. When it fails, even if there is a single exception to its prediction, then you know that, okay, there is something wrong with this, and this has to be superseded by a better theory. So that is also how quantum theory had to be introduced. Because at some point, this ansatz fails to describe all the dynamics that is observable in the physical universe. So here the ansatz is that you compose a function of the position and velocity to describe the state of the system, which is the Lagrangian. How do you construct this function? It is constructed as the difference between the kinetic energy and the potential energy, T minus V. T is the kinetic energy, V is the potential energy. And you describe the state of the system by this difference, not by the energy, not by the total energy, but by the difference in the kinetic energy and the potential energy. And you construct this Lagrangian, and then you determine the integral, the definite integral of this Lagrangian between two times from, let's say, t1 to t2. So you evaluate the integral from t1 to t2 of the Lagrangian, and the Lagrangian that you make use of is t minus v. So if you evaluate this integral, so in earlier times it used to be called as Hamilton's principal function, but after Feynman's formulation, it is now called as action. So action is this integral of the Lagrangian over a time interval. It is a definite integral from time t1 to t2. And the ansatz is that things happen the way they do as per a certain principle which describes accurately whatever happens around you, whether it is a flow of water down the stream or a cricket ball which is hammered by Kohli and how it finds its way to the boundary, or how vehicles move, okay? All dynamics, all motion, how planets go around the sun, okay? All of this happens according to a certain principle, which is a variational principle. The ansatz of that principle is that action must be an extremum. Okay? Now this is amazing. It needs tremendous intuition to discover such a principle. You don't derive it from anything. Okay? Just like you don't derive Newtonian laws from anything, you don't derive this from anything. You can show that it is consistent with Newton's laws, but that's not the same thing as deriving it out of Newton's laws. Okay? So this is an amazing principle which you don't really derive out of anything else. You propose it as an ansatz that, okay, if you begin with this ansatz, then you can provide an accurate description of every mechanical motion that you observe in nature. So this is the principle. And you have now described it in terms of the position and velocity. So you take the simplest functions of position and velocity. A position of function, we know well enough that the potential energy of a particle is a function of position. So it is natural to describe this as the potential. Okay? Function of velocity. Now, if space is isotropic, then property should not be different in different directions, right? So, if there is a function of velocity, you would prefer that function to depend quadratically on velocity rather than linearly on velocity, okay? Because when you take a quadratic function of velocity, it will be v dot v, which is v square, and then it doesn't depend on the direction of velocity anymore. Okay? So you look for a function which depends quadratically on velocity. So you express the Lagrangian as a function of velocity square and a function of position, and the simplest functions in mechanics that you can construct will be t minus v. Okay, why should you have a minus sign there, and why do you have an m over 2 over there is a question which you can naturally ask. Now, this question will be answered a little bit later, but now we should be able to appreciate as to why you express it in terms of the kinetic energy and the potential energy. These are the straightforward functions of position and speed, and you prefer it to be a function of the square of the velocity rather than the velocity itself. Okay, so just keep that point in mind over here, and then we will see why these functions have to be this a little bit later in this course. So this is the Lagrangian, which is t minus v, okay, And if you define the Lagrangian in terms of t minus v like this, you can apply to other things in mechanics, including motion, including interactions which are electromagnetic in nature. You have got a charged particle in an electromagnetic field. You can set up the Lagrangian using a similar formulation. Okay. So Newtonian mechanics depends on the idea of force as the cause of change in momentum, all right? Whereas in the principle of variation, you make no reference to force at all. Likewise, you make no reference to any variational principle in Newtonian mechanics. In Newtonian mechanics, the governing principle is the cause-effect relationship, is the principle of causality. It is the linear relation between acceleration and stimulus and force, right? So that is the governing principle. So the foundations are completely different. Newtonian mechanics makes no reference to variational principle. Variational principle makes no reference to force, but both end up getting you the same results, which is very fascinating. So this is action, all right? And if action is to be an extremum, then a change in action would vanish, right? That is the meaning of an extremum. This extremum can be a minimum, it can be a maximum, it doesn't matter. But if it is an extremum, a change in action because of consideration of choosing alternative paths, that when I push it, it has taken a certain path. Why has it not taken this path? Some alternative path, all right? So when I push it like this, it takes a different path. So when it has taken this path, you can ask, why did it not take this path? So the reason the object goes according to a certain path is because that is how nature governs its mechanics. And we are asking, how do you accurately describe which path will be taken? So the path that will be taken can be different. You can think of, thousands of alternative paths, but only that path will be taken for which action is an extremum. So the variation we are not talking about are with respect to alternative paths in the configuration space, okay? And this variation in action must vanish, and this variation is therefore, since the Lagrangian is a function of q and q dot, it is a sum of these two terms, and this variation must vanish. Okay, so this is the variation, this is the variation in q dot. What is q dot? dq by dt, delta q by delta t in the limit delta t going to 0. So it is a variation in q because of time. What is the variation we are talking about? We are talking about the variation not because of time, but because of alternative paths that the system can take. So the option between alternative paths, that variation is completely independent of taking the time derivative, which also involves a certain variation. It also involves a certain rate, which is dq by dt. It is the rate at which the velocity changes with respect to time, the rate at which the physical property changes with respect to time. That is a different consideration compared to the alternative you get because of the consideration of a different path that you can think about. So these two are completely independent, and therefore these delta q dot is the same as delta of dq by dt. Because these two are independent operations, the corresponding mathematical operators commute. And the reason they commute is because they are completely different operations. One examines the rate of change of position with respect to time, and the other considers a variation because of the choice of an alternative path in the phase space. So these commute. So that is the reason this delta q dot is the same as delta of this is delta q dot, but these two operations change. They can be, these operators commute, they can be interchanged, and you can write this change in the velocity as d by dt of delta q, because these two operations are mathematically independent of each other and the corresponding operators commute. So this is your result now. This is an important result, and we will carry this to the top of the next slide. Okay, so this is the result that we get. And now you have the first term, so the del L by del Q delta Q you have written here, which is the time integral from t1 to t2. The integration is over the time variable, so this is just the first term. And this is now an integral of a product of two functions. And we know how to integrate a product of two functions. Okay, so this is the integral of the product of two functions. So you have del L by del Q dot, and this is the integral of the differential of delta Q. So it is delta Q itself, and you will need to take the difference in the values of this quantity between the upper limit and the lower limit. Means I pointed out that this is a definite integral, so you have to take the difference, and then the second term will involve this d by dt of del L by del Q dot delta Q dt, right? So this is a straightforward integration of the product of two functions, and this is the kind of thing that you are examining. You have got a certain start point, you have got a certain finish point. You can think of these alternative paths. They can even cross themselves, it doesn't matter. So whether it crosses or doesn't cross is just a matter of detail, but they all give you alternative paths. And these are the alternatives which are talked about in the principle of variation. Okay? Where does the variation take place? Between the start and the finish. Not at the start, nor at the finish. Okay? The starting point is fixed. The end point is also fixed. So at this point, at the start and the finish, delta Q is 0. So you are taking a difference of this quantity at the upper limit and subtracting from it the value this quantity has at the lower limit, but delta Q is 0 both at the top of the limit as well as at the bottom of the limit, because the variations are in between, not at the start point or the end finish point. Okay, so this term goes to 0, right? And now you are left with an integral which is from t1 to t2. Del L by del Q is coming from here. From this term you get the derivative of del L by del Q dot. Okay, delta Q is common in the first and the third term, which you have written here. Okay, and the integration variable, integration is over dt. So what is our ansatz? That action is an extremum, no matter what the variation is. Okay, no matter which alternative path is taken. And on all of these alternative paths, delta Q will be different. Okay, the delta Q will be different on all of these paths. So regardless of which path is taken, if this definite integral is to vanish, then the integrand itself must vanish. That is guaranteed, because otherwise you may have this integral go to 0 for some particular choice of delta Q, but that's not what the ansatz is. Ansatz is that no matter what alternative path you take, this action must be an extremum. And this requires the necessary and sufficient condition for this to hold is that the integrand itself is 0, and that gives you what is called as the Lagrange equation. Okay, the integrand is del L by del Q minus d by dt of del L by del Q dot. Okay, so this is the Lagrange equation. It is actually an equation of motion. It describes the evolution of the state of the system. There are time derivatives which are involved. Where are the time derivatives? q dot is the time derivative of position, it is the velocity. Del L by del q dot is the rate of change of the Lagrangian, it is a partial derivative because it depends not only on the velocity, it also depends on position. So for a given position, how does the Lagrangian change with the speed? Okay, so that is del L by del q dot, and its time derivative, how does that quantity evolve with time? So this quantity del L by del q dot is what is called as the momentum. So if you now put in L equal to T minus V, and what is the kinetic energy? Kinetic energy is half mv square. What is the potential energy? It is some function of position. Okay, so if you put this and go back to your Newtonian mechanics, okay, what do you get by writing del L by del Q? Del L by del Q is del by del Q of T minus V. Okay, T does not depend on Q. So it is del V by del Q, but there is a minus sign behind it. And what is the negative change of potential? It is the force. So you get the force out of it. And if this equation is to hold, then it must be, the first term must be equal to the second because the difference vanishes. So the second del L by del Q dot is nothing but dp by dt. Okay, because that's what the force is. So now do you see why you should have that T minus V in the Lagrangian? Okay, it gives you complete equivalence with Newton's equation. Okay, by making this choice, so del L by del Q dot is nothing but the momentum. Okay, but now we will call it as generalized momentum. Now this is a very general formulation, and you know we can cast this problem in more general terms. In mathematics, if you have got a function psi which depends on some quantity xi, whatever it is, okay, we are no longer talking about position, velocity or physical properties. You have got some independent variable xi on which a function, some other function depends. So psi is a function of xi, but it may depend on xi not only directly but also through another function phi, which in turn depends on xi, and it may also depend on the rate at which phi depends on xi. So it depends on the derivative of phi with respect to xi. So that is the nature of this function. It has got an explicit dependence on xi and it has got an implicit dependence on xi through the function phi and also the function phi prime, which is the derivative of phi with respect to xi. And then you ask that, okay, if you construct an integral of this kind, a definite integral, under what condition is this integral an extrema? So you can solve this problem as a problem in variational calculus without making any reference to mechanics of any kind, and it turns out that the condition, necessary and sufficient condition that this integral would be an extremum is given by this, and all you do is to establish the equivalence between phi and q, xi and t, and the integral I with action, and then you essentially get the Lagrange's equation that we just talked about. Okay, so this is a general problem in variational calculus. The equation which is over here is known as the Euler-Lagrange equation. Euler made a significant contribution to that, and the Lagrange's equation in mechanics is just a special manifestation of the Euler's equation, and it explains this particular phenomenon of how would you describe the path along which an object would tumble down to a point, some finish point starting from wherever it does. Okay, it can be under gravity, it can be under some other forces, it doesn't matter. Okay, so we will discuss this analysis in terms of generalized coordinates, generalized velocities, and generalized momenta. So the generalized momentum, we just now identified that del L by del Q dot is the momentum, which will give you the consistent formulation with Newtonian mechanics. And because the generalized coordinate is not always of dimension length, we have already seen that for a rigid body you have got these angles which do not have the dimensions of length. The generalized velocity will not always have the dimension of Lt minus 1, and momentum will also not necessarily be MLT minus 1, but it may have some other dimensions. Okay? So this is the question that we are discussing. You leave out the object at the start and it will come to this point. It is going to take some trajectory along which action must be an extremum. We are interested in finding what is the path the object will take so that it will reach the finish point fastest. That is the Brachistochrone. Okay, Chrone is time, Brachistochrone has to do with the speed, the fastest. So what is the Brachistochrone? What is the fastest path? Okay, that is the question. And you're going to leave this object at zero kinetic energy with no speed. You release it from rest and let it tumble down only under gravity, nothing else. So we choose the zero of the potential scale over here at this point. So the potential is 0 at the start. We have chosen the y-axis to be pointing downward and the x-axis to be pointing from left to right. Okay. So you don't worry about why it is pointing downward or upward, and that is a matter of convention, and we have chosen it this way. Okay. You're going to release it at 0 speed, so the kinetic energy T is 0, and over here V is also 0. And its energy will remain 0. Okay, it cannot change because you're not imparting any energy to it, you're just releasing it. So whatever was its energy at the start will be its energy later, and what is happening is that it will gain kinetic energy, right? But then it will lose potential energy, which is why there is a minus sign, and you have half mv square equal to mgy. Okay, y is increasing downward. Okay, so half mv square is equal to mgy. So that is the relation you get. You're essentially writing only the conservation of energy, there is nothing else. So this tells you what the speed is. Because mgy is equal to half mv square, m cancels and v is nothing but root of 2gy. And the time the object takes to go through an infinitesimal displacement delta s will be that divided by v. So it is, but that distance itself is the square root of delta x square and delta y square. That is just a Pythagoras theorem. So you're not worried about the curvatures because you're taking these intervals in infinitesimal limits. Okay? In infinitesimal limits, delta s will be the square root of delta s square plus delta x square according to the Pythagoras theorem, and you'd extract delta x square as common between these two terms and then take it out of the square root, so that gives you a delta x over here, and then from the remaining terms you get 1 plus delta y over delta x, which gives you a relationship between y and x. So that will actually describe the trajectory. Okay, how y changes with x will give you the equation to the actual path. Okay, and then of course you have the velocity in the denominator, which is square root 2gy. So the curve is now parameterized in terms of y, but you can also parameterize, you wanted to parameterize it in terms of t, but equivalently you have parameterized it in terms of y. Okay, you're interested in finding what is the least time it would take, but you can ask how will y change with x so that this will be the least, so that delta t will be the least, okay? So this is the question that you are developing, right? And the shape of the curve is parameterized in terms of the height function. If you want, you can call it as depth, because you have chosen your 0 to be at the point S, right? Whether you call it as height or depth is a matter of terminology, so I won't worry too much about it. And you are asking, when will this time be the least, okay? So that you have the Brachistochrone. So this is the relationship that you are trying to analyze, right? So let us write this integrand, which is 1 plus dy by dx is y prime, that is the derivative of y with respect to x. And this integrand is what I have written as psi, which is a function of y. There is a y sitting in the denominator under the square root sign, and there is a y prime over here. So this integrand is actually a function of y and y prime. This is your function psi. This is the integral. And this is your total time interval, okay, which is from start to finish, and the path will be such that x will go from the start, which is 0, to the x coordinate of the final point, which is the finish point. Okay, so the integral over time can be evaluated as an integral over x. Okay, so let us look at what is the derivative of psi with respect to x. So it will depend on how psi depends on y, del psi by del v, del y, and then how y depends on x. Plus, this is just the chain rule of taking the derivatives, and how psi changes with y, which is del psi by del y prime, and how y prime itself changes with x, which is dy prime by dx. Okay, so this is d psi by dy times, this is nothing but y prime in our notation, and this is the derivative of y prime with respect to x, which is nothing but y double prime in our equation. So these two terms we now move to the left. So you have got this quantity minus this, which should go to 0. Okay, so you have 0 equal to d psi by dx minus d psi by dy prime, y double prime, which is this term, and minus y prime del psi by del y, which is this term. Okay, so we have got it straight out of this simple relationship. And these three terms you can write easily as the derivative of what is in this box. Okay, because this is the derivative of a product of two terms, and that's what gives you two terms over here, right? So let us take this result to the top of our next slide, that 0 is equal to the derivative of this. So obviously whatever is the quantity in this box, in this rectangle, must be a constant. Okay, because its derivative with respect to x vanishes. So this is the constant. Psi, we know, is this function of y and y prime. Okay, and we can find what is the partial derivative of psi with respect to y prime, because we know how psi depends on y prime. The dependence of psi on y prime is in this term y prime square, but then of course 1 over root 2 gy will come as a constant, and then this itself comes under the square root. The derivative of 1 will vanish. So you take the partial derivative of psi with respect to y prime, and that is nothing but y prime over root 2 gy 1 plus y prime square, right? So what does it give you? So you've got psi minus, what is psi? Psi is this quantity, so that comes over here, minus y prime, which is this, and then you have del psi by del y prime, which is this, and this must be equal to this constant, which is kappa. Okay, so this is the problem we are trying to tackle, and we have now described the condition that must be satisfied, and you just manipulate these two terms, combine them by finding the common denominator, okay, and you have a simpler relationship, which is given over here, and you get y plus y prime square equal to this. But g is a constant. It is an acceleration due to gravity at that particular point, so it's not going to change. Kappa is already a constant. So 1 over 2g kappa square is also a constant, and we can call that constant as 2 beta. Okay? So y prime must be equal to root of 2 beta minus y. So you subtract this y, move it to the right, get 2 beta minus y, and then divide by y, take the square root, you get a y prime. So y prime must always be greater than 0, because once the marble starts rolling, there is no reason why it will reverse its direction. Okay? There are no lateral forces. So dy by dx will always have to be positive. And if dy by dx is to be positive, then the right hand side of this equation must also be positive. That tells you that 2 beta must always be greater than or equal to y, and we know that y itself always has to be greater than or equal to 0 because you started out with 0 and y is only increasing as you go down, right? So you get this inequality relationship between y and beta, that 2 beta must always be greater than or equal to y, which is also greater than or equal to 0. So this is the relationship that you get, and you transfer the variable one more time. We already transferred from t to y, and now from y to theta by introducing this relation. You write y in terms of theta now as beta into 1 minus cos theta. But then at y equal to 0, cos theta will be equal to 1, and therefore theta must be 0. So you find that second constant. Okay? So you have this relation that 2 beta must be greater than or equal to y, which is greater than or equal to 0, and dy by dx is now given by y prime, but y is written in terms of theta. So you can get y prime, from here. So you get 2 beta, you're taking the derivative, right? So you get 2 beta, and this is a very simple manipulation of this. You write these functions not in terms of theta, but in using trigonometric identities. You can write it in terms of theta by 2, and you get this relationship which I bring to the top of this slide, and you have dy by dx, which is y prime equal to the ratio. This is the inverse tangent of half the angle. Okay? So what it tells you, that dy itself is this ratio multiplied by dx. Okay? And y itself is given by beta minus beta cos theta. So that tells you what is dy. A differential increment in that quantity will appear as a differential increment in theta, right? And from the earlier relationship, you have this result, that 2 beta sine square theta equal to dx, right? So now you can put these two results together and get dx equal to beta 1 minus cosine theta, and now if you integrate this, you will get a relationship between x and theta. But when you integrate, you will also get a constant of integration, which is c. You can determine that constant of integration by recognizing that at x equal to 0, theta must be 0. So by putting that condition, you determine what that constant of integration must be, and that constant of integration obviously turns out to be 0. So now you have got the relationships both for x as well as y. So y is written in terms, is in this box, and x is over here with c equal to 0. So you can write x and y, and now you have got a very beautiful relationship. And you just have to identify the curve which is described by this. Okay? So what is beta? That is something that you want to determine, and if you can find that out by demanding that beta must be such that the path should not only begin at the start point, but it should go through the final point. Okay, so the extremum were pinned down already. Okay, so it has to go through the final point, and you can easily see that if you write this beta as the radius of a circle which is sitting over here, then you have an equation to a cycloid. So it's a matter of straightforward trigonometry and geometry. I will leave that as an exercise, but you see that the resulting equation that you get is an equation to a cycloid. So you know what a cycloid is, and I think I've got a video which I downloaded from the internet. What happened to that? Yeah, I think it's coming. Yeah. So this is the cycloid. So it is the path of, let me put it on repeat and show it again. So if you have got a circle whose center is moving in one particular direction, then a point on the rim will trace the cycloid. So that is the trajectory that will be taken by this object. So this is what is called as a cycloid. So let's go back to this. So you essentially get a cycloid trajectory, and here are the paths that we started out with, that you can think of alternative curvatures, okay, and you can think of infinite ones. And the models that I'm showing you, these have been prepared and tested right here in Tirupati by our students. 3 students from ICER carried out this experiment, Parth, Abhiya and Vaishak. And there is a report on this which is available in Resonance, which you can look up. So these models are available. What you do is you drop a marble from that point, and you release it by an electromagnetic magnet so that everything is automated. And then you time it using photodetectors. So you've got a light beam crossing, and as soon as it crosses the light beam, the time is recorded. And then when it crosses the point B, the time is recorded. And you can record these time intervals along alternative paths. So we fabricated 4 shapes. One was a straight line, one is along the Brachistochrone, okay, which is the equation to the cycloid, one which is slightly shallower than the cycloid, and one that is somewhat deeper than the cycloid. And you can do this experiment. And these students did this experiment like hundreds of times, and then take the average to make sure that there are no experimental errors of any kind and so on. So very carefully done experiment, and they indeed found that when it goes according to the cycloid trajectory, the path is minimum. So I think we should be setting up this experiment in our lab as well, so we'll do it. But for the time being, I will stop this class today. I will end the class today, and we will discuss further applications of the variational principle. But it's nice to see the Brachistochrone, the solution to the Brachistochrone, very famous problem posed by Bernoulli and answered by the lion, who was recognized by his claw. So thank you. If there is any question, I'll be happy to take. So otherwise, goodbye for now,